Jai Hind to all. Today I am here to present the fifth video lecture of the series Digital Signal Processing BEC 503, and the topic of today is multi-rate digital signal processing. So here in this particular video lecture we will see what is the multi-rate digital signal processing and what are the processes that is included in multi-rate digital signal processing. So if we'll see, then multi-rate digital signal processing can be in terms of introduction, you can see that it can be like in many practical applications of DSP, we are facing the problem of changing the sampling rate. You know the sampling rate. For perfect reconstruction of signal, sampling rate should be greater than the highest frequency component present in the signal. Okay. So what is the requirement of multi-rate DSP? Like we are having a signal and we want to sample it at a rate which is far greater than you can say sampling rate. Let us suppose we are having an audio signal which is and bandwidth is 4 kHz, and generally we choose a rate 8 kHz, but which is you can say the Nyquist rate also for that. So we will choose 8 kHz signal as a sampling frequency. Like another thing is that if we want more quality in the reconstructed signal, then we can sample it up to 12 kHz also, 16 kHz also. So this is about the sampling rate chosen for a particular signal. Okay, so that's why we require the sampling rate. At some place we require that our sampling rate should be increased or it should be decreased by some amount. Okay, generally we prefer that this amount is an integer value, okay. But if we will combine both these type, then we can also obtain our sampling rate, which is the multiplication of combination of these two. Like we will see later on that we will see later on this. So the process of converting a signal from a given rate to a different rate is called sampling rate conversion. Okay, so this I have discussed. So in turn, systems that employ multiple sampling rates in the processing of digital signals are called multi-rate digital signal processing systems. So we call our system as multi-rate digital signal processing systems if that system uses multiple sampling rates. Okay, so if it is using multiple sampling rates for the processing of digital signal, then we can call that system as multi-rate digital signal processing systems. Okay, so because we are in DSP, we are dealing with the discrete time systems. So discrete time systems may be single rate system or multi-rate system. Means we can take a signal, and sample that signal at a single rate, or we can choose multiple rate also for that. Okay. Okay, so the systems that use single sampling rate from A to D converter to D to A converter are known as single rate systems. Why the concept of A to D and D to A comes over here? Because generally the 90% of the signals, 99% of the signals that are real time signals we use are analog signals. Okay, so before conversion, processing is required. Okay, so we are having an analog signal, so A to D converter is required to convert that analog signal into digital signal. And again, D to A converter is required after processing to get back that original analog signal. Okay, are known as single rate systems. So these are single rate systems, and the discrete time system that process data at more than one sampling rate are known as multi-rate systems. So similar thing is there. Now different sampling rates can be obtained using an upsampler and downsampler. So here we are discussing that how we can increase the rate. So upsampler means simply you are having, let us suppose you are having a signal xn and you want a signal output yn, which is equal. Let us suppose here the rate is let's say t1, and you want rate here as t2. So t2 should be equal to 2 times of t1. It means we want to increase the rate by an amount twice. Okay, so upsampler is denoted by this arrow, and here we will write the value 2. Okay, so we will get the signal yn, that will be the twice of the rate of the signal xn. Okay, and similarly in case of downsampler, let us suppose similar thing is there, but here Downsampler is denoted by this type of symbol, and the output yn. In this case, T2 will be equal to T1 by 2. Okay, so this is the concept of upsampler and downsampler. So the basic operations in multirate processing to achieve this are decimation and interpolation. So now let us come to the point decimation and interpolation. So decimation is and interpolation are the process, and the device that perform these decimation and interpolation are called as decimator and interpolator. Okay. So you can see here, this is upsampler, this is downsampler, but when we will discuss about decimator or interpolator, then you will find that there is something change in the diagram. We will see later on. So decimation is for reducing the sampling rate and interpolation is for increasing the sampling rate. So from here we can understood that this process may be called as interpolation process and this process may be called as decimation process. But if we'll talk about the block diagram, so this is the block diagram of upsampler and this is for downsampler. Okay. So now come to the point decimation. So in this particular video lecture, I will include the process of decimation in detail. We will see the mathematical expressions, we will see the derivation, that how this sampling rate is reduced in the process of decimation. Okay. So reducing the sampling rate of a discrete time signal is called downsampling. Okay. So you know downsampling I have already discussed. The sampling rate of discrete time signal can be reduced by a factor d by taking every dth value of the signal. Simple thing is that, like, look here, this is the figure of a downsampler. Here the signal is xn and the output yn is x times x of d times n, where d is an integer, value. Okay. So what happened? Let us suppose check for a signal. We are having a signal, input signal xn, which is written like 1 2 3 1 2 3 1 2 3 like this. Okay. So now you will check the value of x of 2n. Let us suppose d equals to 2. So this is the case where d equals to 2, x dn. So you can say d equals to 2. So you can say x 2n means at n equals to 0, what is the value? X0 is 1 here, and here again if you will put n equals to 0, you will get value again x0, that will become 1. Now if you will put n equals to 1 over here, the value is x1, which is this, but when you will put n equals to 1 over here, you are having value x2. So x2 is this 3. So that's why when you will change the value of n, you are getting the values like this. So you can see here in the output side, we are having samples, we are removing one samples in between the samples. These samples are reduced. So you can say when d equals to 2, then d minus 1 samples in between the samples are eliminated. Okay. So look here, you can say 1 3 2 1 3. So we are eliminating d minus 1. If the value of, here you can see the value of d is 3. So when the value of d equals to 3, then you will get the first value as x0, second value is x3, then x6, x6, then x9. So you are having this type of output. Okay. Again you can see here the value of d is 3, and again here their d minus 1 samples are eliminated, because the value of d minus 1 is equal to, in this case, is 1 and here it is 2. So you can see after first sample we have removed these two samples, then these two samples and these two samples. Okay. So this is how downsampler works. Okay. Again you can see the example of the previous one, where d minus 1 samples are removed in between the samples. This is the original signal xn, this is x2n. You can see this sample is eliminated, but index will become same. Here index will become same, but the next value that you will get here it is 2, like this. So this is for d equals to 2, and similarly the graph for d equals to 3 is like this. Okay. So this is the graphical representation of the same sequence here, which is given over here. Okay. Now we will see decimation by a factor d. Okay. So look, from here you can see that if we want to reduce the rate, then simply we have to pass it through a downsampler. and we will get the reduced rate. But this process is not so much simple. If we will directly simply downsampling the signal, then there will be some issues. So that's why decimation process is somewhat different. What is the difference? We can see from here. Like, so I am starting here from the derivation, decimation by a factor d. So let us assume that we are having a signal xn with the spectrum x omega is to be downsampled by antigen factor d. Okay, simply we are having a signal xn which is band limited signal, and spectrum is x omega for that. Now we are assuming that this x omega is assumed to be non-zero in the frequency interval 0 omega pi or equivalently mod of f less than equal to fx by 2. So you can say 0 omega pi, or you can also put mod over here. So it means this signal is non-zero in both the direction. You can say between minus pi to pi, you can say it is non-zero, otherwise it is 0. Okay, means you can say our spectrum is band limited, or the signal that we have taken is band limited signal. Okay. So we know that if we reduce the sampling rate simply by selecting every dth value of xn, the resulting signal will be an alias version of xn with a folding frequency of fx by 2d. So here basically we want to say that if we will simply remove the one sample in between the samples, then it will lead to aliasing effect. Now we will see how it will happen. Okay, so to avoid aliasing, we first reduce the bandwidth of xn to f max equals to fx by 2d, or equivalently omega x equals to pi by d. So here we are simply saying that what happened in the process of decimation, we are compressing the signal in time domain. So when the signal is compressing in time domain, correspondingly in frequency domain it will become expanded. So what happened, if you are taking the original signal like 0 to pi, then in that case when you will do the decimation process, then the spectrum will become 0 to pi d or minus pi d to pi d. So it will become aliasing. Okay, so aliasing effect will be there. So how we will reduce this? We know that our spectrum is stretched by a factor d. So what we can do this? So what we can do this? We can simply do this. We are having this signal xn. So rather than working on xn, if we will simply reduce our signal, okay, if we will simply reduce our signal, then this spectrum will automatically become, if this signal become reduced, then its spectrum within the range, it will not be the alias version. Okay. So that's why what we are doing here, the maximum frequency that we are taking, rather than pi, we are taking it as pi by d. So when it will become stretched, it will reach up to pi. Okay. So the aliasing, then we downsample by d and thus avoid aliasing. So this aliasing problem can be eliminated by band limiting input signal by inserting a low pass filter called anti-aliasing filter before the downsampler. So the process is simple. You can see from here what we are doing, rather than directly applying this signal xn to this downsampler, what we are doing, because we know if we will directly pass this signal through this downsampler, then the spectrum will become stretched. Spectrum will become stretched and it will lead to the aliasing effect. So what we are doing? We are restricting the bandwidth of this input signal xn initially. We are reducing its bandwidth so that it will reduce, and when it will become expanded due to this downsampling, then it will be balanced out. Okay. So that's why the block diagram of decimator, which is a device, is completely this, and this process is called as decimation process. So here you can see before downsampler what we have done, we have taken signal xn which is having bandwidth let's say pi, 0 to pi, and we are passing it through a low pass filter. We are passing it through a low pass filter. Why we are passing it through low pass filter? So that its bandwidth will become restricted. After restriction, when we will apply downsampler, again we will get the reduced rate. Okay. So here, so this process is illustrated in this figure. The input sequence xn is passed through a low pass filter characterized by the impulse response hn and a frequency response hd omega, which ideally satisfies the condition. So what we are assuming over here is that this decimation filter that we are using, which is a low pass filter having frequency response, this means within this range it will give you the value, otherwise it will give you 0 value. Okay. So what happened when we will pass our signal xn having bandwidth from minus pi to pi through a low pass filter having bandwidth minus pi by d to pi by d, because this mod is there. So, the signal after this decimation having bandwidth minus pi by d to pi by d only. Okay. So, thus the filter eliminates the spectrum of x omega in the range pi by d mod omega pi. It means what happened between minus pi to minus pi by d, you will get 0 output, and after pi by d to pi, you will get 0 output. Okay. So, of course, the multiplication is that implication is that only the frequency component of xn in the range mod omega less than pi by d are of interest in further processing of the signal. So, from here we can see that we are having input signal rate fx and output signal having rate fy. So, this fy is fx by d. So, you can see the rate is reduced by a factor d. Now, we will see the detailed mathematical description. So, here the input is applied to a low pass filter. So, this is corresponding to convolution operation. So, what is the relation between Vn and Xn, if you will see, where Hn is basically the impulse response of the filter. So, you can say this is the convolution operation, and after convolution this is the downsampling operation. So, we will see the mathematics here. See, the output of the filter is a sequence Vn which is given as. So, Vn we are having here, Xn we are having here, Hn is the impulse response of the low pass filter. So, we can write as Vn equals to summation k equals to 0 to infinity. We are taking only one side. Okay, you can take it both the side, but I am assuming only one side. So, hk into x of n minus k, this is the convolution. So, the output signal Vn that we are obtaining after passing through low pass filter is nothing but Vn, which can be represented by this expression. Now, we are downsampling this by a factor d to produce ym. So, what is the relation? Ym equals to v times md. Okay, ym equals to v times md. So, the output here will become ym equals to v times md. Now, you will put md in this equation. So, you are having the value hk, and in place of n you are putting md. So, x of md minus k. So, we are having this expression. Okay. So, from here you can see that the filtering operation xn is linear and time invariant, the downsampling operation in combination and with the filtering result in time invariant system. So, what happened? This is a linear system. Okay. The process of convolution will become time invariant, but when we include convolution operation with this downsampling operation, then the overall process will become time variant operation. Okay. So, this is the case here. So, consequently, the overall linear operation, linear filtering followed by downsampling action is not time invariant. Okay. So, it is time variant operation. Now the frequency domain characteristics of the output sequence Ym can be obtained by relating the spectrum of Ym to the spectrum of the input sequence Xn. Now, what we are going to relate, basically we will see what type of spectrum in this signal Xn, and what type of spectrum we are getting over here, and what type of spectrum we are getting over here. Okay. So, for mathematically justifying it, initially we are assuming a sequence V tilde n. Okay. So, V tilde n is like Vn, where n equals to 0 plus minus d plus minus 2d, otherwise 0. It means you can say you are representing your V tilde n only for those values of Vn where n is a multiple of plus minus d. Okay. So, clearly V tilde n can be viewed as a sequence obtained by multiplying Vn with a periodic train of impulse. So, how we can get it? How we can get this relationship? If we will multiply this signal Vn through a impulse train, wherein the impulses are located at 0, d, 2d, 4, 3d and in minus side also, then you will get the same output. Okay. So, the discrete Fourier series representation of Pn is, so now here I am presenting the discrete Fourier series representation of the impulse signal, impulse train. Okay. So, this is what Pn equals to 1 upon d, summation k equals to 0 to d minus 1 e to the power j 2 pi kn by d. So, similarly, V tilde n is Vn into Pn. So, Ym equals to V tilde md simply, and you can write it like Vmd into Pmd, and this Pmd is equal to 1. So, we are simply getting the value Vmd. Okay. So, Ym equals to V of Md. Okay. So that is why from here we are getting the output that we are obtaining for this signal Yn, which is equal to V times Md. Okay. Now, we can see the jet transform of the output sequence Ym. So, output Ym jet transform. So, you know simple definition of jet transform, Yz equals to summation m equals to minus infinity to infinity Ym into z to the power minus m. Now, we have already obtained Ym equals to V tilde Md. So, we have put the value V tilde Md over here and into z to the power minus m, and then what happened? We are simply putting here after this step to this step, we are simply putting Md equals to m. So, when Md equals to m, then m will become m by d. So, that is why this expression is changed V tilde m into z to the power minus m by d. Okay. Okay. So, where the last step follows from the fact that V tilde m equals to 0 except at multiples of d. So, this is the output that we are getting over here. Okay. Now, we have further simplified it, because V tilde m is Vm into Pm, Vm into Pm. Suppose n is replaced by m, so this is Vm into Pm, and Vm Pm is nothing but 1 upon d summation k equals to 0 to d minus 1 e to the power j 2 pi k m by d. So, that is why we have done this thing only. So, Vm into Pm, okay, and z to the power minus m by d is also there. Okay. Now, we can take 1 by d outside from this equation, and we are taking this term outside, okay, here, and then this summation came here, and Vm into e to the power. Now, what we are doing basically, here minus sign is not there, but I am putting minus sign over here, e to the power minus j 2 pi k by d. So, m is alone from here, and z to the power 1 by d I am taking from here. So, that is why minus this e to the power minus j 2 pi k by t into z to the power 1 by d up to the power to the power minus m will be the output. Okay. So, now you can assume it like 1 upon d summation k equals to 0 to d minus 1. Now, what is this? Summation m equals to minus infinity to infinity Vm into z to the power minus m, where z value is nothing but this whole value. Okay. This whole value, and in form of symbolic representation, we can write it as like Vz. So, that is why this z is represented over here, V into V of e to the power minus j 2 pi k by d into z to the power 1 by d. Okay. Why I am writing this? Because Vm into z to the power minus m, we can write it symbolically like Vz. So, that is why in place of z, this term will be there. So, we have written this term over here. Okay. Now, Vz, this is Vz, let us say. Now, see what is Vz. From here, in this block diagram, if you will see this in frequency domain, then what is the value of Vz? If I am taking the z transform, I am taking this part only and taking the z transform. So, Vz will become Hz into xz, xz into hz will become vz in frequency domain, because the convolution operation in time domain corresponds to multiplication in frequency domain. So, that is why we are getting this vz equals to hz into xz. Now, in place of z, this term will be there. So, hd e to the power minus j 2 pi k by d z to the power 1 by d, and similarly x e to the power minus j 2 pi k by d into z to the power 1 by d. So, this is basically the output yz, because so this I have already told that how we are getting this last step. Now you know, if you want to if you have need the spectrum of the output signal. So, spectrum means frequency spectrum, frequency spectrum means magnitude spectrum and phase spectrum. So, what is the relationship between Z transform and DTFT? Because we are taking a discrete time signal, so corresponding transform will become discrete time Fourier transform. So, if discrete, what is the relationship between discrete time Fourier transform and Z transform? If you will see closely, then you find then DTFT is nothing but the Z transform which is evaluated over unit circle. if the Z transform evaluated, we evaluate over unit circle, then it will become nothing but dTFT. So this is like here Z equals to R e to the power j omega. Now if this R equals to 1, so Z can be represented by e to the power j omega. So this is the conversion, you can say, of Hz to H e to the power j omega, which is nothing but the frequency spectrum. Okay. So now what we are doing, we are evaluating Yz in the unit circle. We are evaluating Yz in the unit circle to obtain the output signal Ym. Okay. So what we will do, Yz we are having, we will put Z equals to e to the power j omega in this particular expression to get the spectrum of the output signal. Here we have obtained just the output in Z domain. Okay. So this okay. So this Yz will become, we conclude that spectrum. Now Z equals to e to the power j omega, but we are discussing this in correspondence with the output, and in case of output we have taken the value as Fy. So in radians it will become omega y. That's why you can see this expression. We conclude that the spectrum y omega y, which is obtained by evaluating on the unit circle, can be expressed as, so we are simply expressing it in frequency domain. Okay. So you can see here, you will put Z equals to e to the power j omega, Z equals to e to the power j omega, then when you will put, so it will become e to the power j omega by d, then you will take common, so it will become e to the power j omega by d minus 2 pi k by d. Okay. So you are having this term. Okay. So you are having this term. If you will put over here, you are having this term. Okay. And here this is basically the symbolic representation. This is not the exact value, because h e to the power j omega can also be written as h j omega. These are just the conventions. So according to this, we are having this. Now, if we are choosing a filter which is designed properly, then this frequency response will become, there will be no aliasing. So aliasing is eliminated. So that's why these terms are creating the aliasing. So that's why these terms will become 0. So the output y omega y equals to 1 by d h d w y by d into x w y by d. Now if we are designing, if we are choosing an ideal filter, let's say, so the value of this h d omega y by d is nothing but equal to 1. So we are having this output 1 by d x w y by d. Okay. So now we can see the spectra of input intermediate signal Vn and Ym that are illustrated in figure. So we are having this input signal. This is our input signal, which is representing between minus pi to pi. Okay. Now we are passing this signal from a low pass filter having bandwidth minus pi by d to pi by d. Okay. So when we are passing this signal through this low pass filter, we are having this output v omega x. Okay. Because rate is not changed yet. So because of this, we are having a spectrum of VWX signal as minus pi by d to pi by d, and then output YWY, what happened when we will do the downsampling operation, then this spectrum will be stretched. So we are having the output minus pi to pi. Okay. So this is about the aliasing effect. So aliasing is nothing but, if we will not restrict the bandwidth of the input signal, then what happened? The spectrum will be stretched, and if the spectrum will be stretched, then there will be overlapping like this. So this is nothing but the aliasing effect. So for avoiding this, what we have to do? We have to just initially we have to just restrict the bandwidth of the input signal. Okay. So these are the references. Thank you so much. Thank you.